Before we get into Gibbs free energy, I want to remind you about what our purpose is, and that is to be able to decide if a chemical reaction or another process, but reactions for us, is spontaneous. And if it's spontaneous, that means that it occurs naturally without you having to put any energy into it. And if it is spontaneous, it means it can be used for work. If it's non-spontaneous, it means something that you would have to put energy into to make it work. And the rule is that if entropy is increasing, so if we have an increase in entropy, then the reaction is spontaneous. The thing is, when we say this, it needs to be entropy of the universe. And by that, we mean not just the substances that are undergoing the reaction, but also the surroundings around that may be heating or cooling due to the reaction. Remember that if you're warming something up, its entropy is increasing. So we have to take both of those things into account to decide if a reaction is spontaneous, to decide if entropy is increasing for the universe. So we have this equation that puts those two parts together. This first term is the change in entropy for the substances that are reacting. And the second term, it's misleading because it says heat of reaction. But remember, we took a negative sign there because this really has to do with the heating or cooling of surroundings. So this equation puts those two together as far as, deciding what's happening to the universe overall. Over here, it's spontaneous if the change in entropy for the universe is a positive number. And then we're going to take this equation and we're going to kind of rearrange it in order to define Gibbs free energy. And the first step that we do is that instead of having this delta S here for the universe, I'm just going to put in a 0 and say that this term has to be a positive term in order for the reaction to be spontaneous. So if this is true, if these are greater than 0 when you add them up, then the reaction is spontaneous. And then, and I kind of made a mark over here, we're basically just rearranging this equation, and what we come down to here is we get this. And so this is flipped and rearranged, but basically this says that if you add these up and you get a negative number, then the reaction is spontaneous. And so this, you guys, this is the definition of delta G. So it's a derived function based on entropy increasing for the universe. Change in Gibbs free energy takes into account both the changes for the substances and the changes for the surroundings that are being warmed. So I'm going to rewrite this here. And again, these little degree signs are just saying standard state, because when we start looking up values on tables, they're going to be at set temperature. Remember that thermodynamic properties really change with temperature. And so our thing was, if we look at this last equation, we flipped the sign because we multiplied by -1. So we need this part to be less than 0. So change in Gibbs free energy must be negative for spontaneity. And so this is the test we will use to decide if a reaction is spontaneous or not. We won't go and calculate the change in entropy for the universe. We will use Gibbs free energy. At a problem where we calculate the change in Gibbs free energy using these thermodynamic values, we're going to use this equation. And then we can see what we get for our Gibbs free energy to decide if the reaction is spontaneous or not. We will calculate each of these one at a time using the method that we've done before, where you basically add up the values for the products and subtract the values for the reactants. There's a delta there. Remember that this n, these n's, those are from the coefficients. And they're in moles, and we'll keep track of the units that way. And because the moles from the coefficient cancels with this moles, this comes out in kilojoules. So I'm just going to put it off to the right. And again, I don't always write it there, but these values are standard state. And so really, I could have a degree sign because this is going to vary with the temperature and pressure. So I have my first value. And let's go ahead and interpret that. Is this reaction endothermic or exothermic? Okay, let's do the same thing with the entropies. Again, there should be degree signs on these. I don't always show them all the way down, but and the unit on entropy is joules. If we come up here, it's joules per K mole. The mole is canceling on this because of the coefficients in. Again, these are the coefficients from the equation. So the units on this whole part are joules per K. Okay, and so we have our next value, and I want to say, so we've been talking about entropy has to increase, and we're looking at this number and saying, oh, okay, what's happening here? Remember that this number is only for the substances. It's not the entropy of the universe. And so we can't use this to decide if the reaction is spontaneous or not. This is just the substances. And let's see what else we say. Okay, let's put those together now. And something we really have to watch for is that our heats of reaction are in kilojoules, but our entropies are in joules. So it's a good idea that once you get this, let's just go ahead and convert that to kilojoules per K. Flip that. Okay, before we plug in, because we need that to match. And for the temperature, remember we're using this standard state. When we use these signs, it means we're at 25 degrees C, which is 298 Kelvin. So that's the temperature we're going to use in this equation here. And then of course this K cancels and they both are terms in kilojoules. So we got our Gibbs free energy. Is the reaction spontaneous? Gibbs free energy is negative. That means that the change in entropy for the universe is positive, because that's what Gibbs free energy takes into account. When Gibbs free energy is a drop, just like when enthalpy decreases and we have a negative sign, we call it exothermic. But with Gibbs free energy, we call it exergonic. And the opposite of that is when you have a positive delta G, we call that endergonic. Okay, so that reaction is spontaneous.